We are still in the second section in user-centered e-design for innovative technologies and services. And now the floor can go, now Aldo, Sorniotti, the floor is yours. You can start with the technical session, and the University of Surrey is a Steve partner, and the University of Surrey work on energy efficiency from a very technical point of view. So please, Aldo, can you go through your presentation and add, of course, more interesting information to my few words.
Thank you very much, Francesca. Can I share my screen? Because
yes, of course, I'm doing this.
Okay, can you see my screen now?
We can see your screen. We can hear you well. For your information, again, we can't see your face, so it's
I think if it is fine with you, as a limited bandwidth, I will go just with the screen share by my face.
No problem. Okay.
All right. So I'm very pleased to deliver this short presentation about the technical developments, the selection of technical developments on the Steve electric quadricycles. In particular, this presentation will focus on the energy efficiency and safety aspects. When we prepared the proposal, the Steve proposal, we noticed that there was the availability of tests of these L6, L7 quadricycles showing very poor active safety performance. These are some pictures from an article of the Italian magazine Quattro Ruote, where they tested some of the quadricycles available on the market during braking tests. We can see that because of the very low wheel base and the significant height of the center of gravity, we have a wheel lifting in some cases on the rear axle. Also, we have quite frequent wheel lifting in cornering conditions. One of the targets of Steve is to try to improve the active safety aspects of these quadricycles. In particular, in Steve, this was facilitated by the fact that the JC quadricycles, both in the version originally manufactured by JC and in the modified version by ELAF with ELAF in-wheel motors, are characterized by in-wheel motors. So it is possible to have individual control of the wheel torque levels. So this presentation will cover some examples of algorithms to enhance the vehicle dynamics performance and reduce the energy consumption for these quadricycles. In particular, I will start this presentation with an example of controller that has been implemented by my team together with Tecnalia during Steve for energy efficient torque vectoring. So for energy efficient with torque distribution for the electric quadricycles with multiple motors. Just to make you understand, if you are not familiar with torque vectoring control technology, torque vectoring means that it is possible on a vehicle. Here we can see a simplified top view of the vehicle with the four corners, where we can have, for example, two in-wheel motors in the case of the Steve quadricycles on the rear axle, or four in-wheel motors if we have a four-wheel drive vehicle. But essentially, with a vehicle with multiple powertrains like the Steve quadricycles, it is possible to generate not only a traction force through the motors, but it is possible to have a different value of longitudinal force between the tire and the rod on the two sides, on the left and right hand sides of the quadricycle. And by doing so, it is possible to generate a so-called direct yaw moment that allows to control the stability of the vehicle in cornering conditions. And in particular, if we want to generate a given traction force and a given yaw moment, it is possible, especially in four-wheel drive configurations, to have an infinite amount of wheel torque distributions to achieve this target. Moreover, in Steve, we had also an energy management objective in terms of reduction of the energy consumption during a typical driving cycles in straight line, but also in cornering conditions. And therefore, the technical ambition of Steve was to combine the torque vectoring control aspects, focus on the enhancement of the cornering response to the electric quadricycles, with the energy efficiency side, with the energy management. For example, here I'm reporting an efficiency map of a typical electric motor. So the first thing we did in Steve, from the viewpoint of torque vectoring control, was the definition of an energy efficient cornering response to the vehicle. This diagram, that is based on the tool that was developed within the project, reports the steering angle at the wheel as a function of lateral acceleration, and in particular the red line shows this characteristic for the passive vehicle, so for the quadricycle with the same wheel torque on the left and right hand sides, and then by playing with the torque distribution between the left and right hand sides, it is possible to find an actuation that minimizes the powertrain input power, that minimizes the power consumption of the vehicle. So the green line that I'm indicating now with the mouse corresponds to the optimal so-called understeer characteristic of the vehicle. So for each lateral acceleration, by implementing a cornering response through torque vectoring that corresponds to the green line, it is possible to reduce the power consumption of the vehicle. And in particular, this carpet plot shows for each lateral acceleration and each dynamic steering angle how much the consumption, the power consumption, would increase in percentage with respect to the optimal configuration, just to give you an idea of the potential reduction of power consumption by playing with the left to right wheel torque distribution. I would like to point out that in the tool that was developed within Steve, we considered the whole set of power loss contributions of the vehicles that are relevant to torque vectoring. So we not only consider the powertrain power losses, but also we considered in our energy efficient algorithm the power losses that are related to longitudinal and lateral tire slip. And in particular, this second carpet plot reports the dynamic steering angle as a function of lateral acceleration, and the color indicates how much the powertrain power losses are with respect to the total power loss when including the tire slip power losses. So essentially, we can see that in a very small lateral accelerations of the vehicle, we have that the powertrain power loss account for 75% of the relevant power losses for torque vectoring control, whilst when we push the vehicle to medium-high lateral accelerations, the magnitude of the powertrain power losses is only 40–45% with respect to the total power losses. And through these tools developed in cooperation with Tecnalia, we implemented for the Steve quadricycles maps like those that are reported in this slide for the reference yaw rate of the car. The yaw rate is the angular speed of the car about the vertical axis. So essentially, it tells us how much we want the vehicle, the quadricycle, to corner. In particular, here I reported an example of reference energy efficient yaw rate map for as a function of steering wheel angle for different values of vehicle speed on the left. And on the right figure, we can see an energy-efficient reference yield rate map for the Steve quadricycles as a function of steering wheel angle for different values of longitudinal vehicle acceleration. So the first achievement was the definition of an energy-efficient reference cornering response. And then, in terms of implementation of the controller achieving this reference energy-efficient cornering response, we have implemented state-of-the-art nonlinear model predictive control technology for energy-efficient torque vectoring. So, in very simple terms, this is a controller that minimizes a cost function, that minimizes an objective that is expressed by a mathematical function, subject to the dynamics of the model of the vehicle. So essentially, the controller predicts the future behavior of the vehicle by using an internal model that runs within the controller. And the controller considers also the constraints. For example, typical constraints are in terms of limits of motor torque, maximum and minimum motor torque. And in particular, just to give an idea, I reported the cost function that has been implemented in the torque vectoring controller for the Steve quadricycles that includes multiple terms to consider different vehicle dynamics, drivability, energy consumption objectives. In particular, we have a first term that is underlined now in the slide that has the target of tracking the reference torque demand. We have a second term that has the target of tracking the reference energy efficient yield rate. We have a third term that is about vehicle safety and stability because it tries to limit the rear axle side slip angle. Then we have the power loss terms that contribute to the energy efficient behavior of the vehicle, that are the power loss term of the powertrains, the power loss term in terms of longitudinal and lateral tie slips. And then just to make the controller general, we have also considered, in case of a future development in terms of forward drive layout, we have also considered additional terms that are optional for the energy efficient front to rear wheel torque distribution in case there are also in-wheel motors on the front axle. And moreover, this algorithm not only considering the cost function, all these contrasting objectives, but the weights, so these coefficient W's that are present in the cost function formulation dynamically vary during each maneuver based on a fuzzy logic algorithm in order to prioritize energy efficiency when the vehicle is not operating at the limit of handling, when the condition is not safety critical, and to prioritize vehicle safety when the vehicle is operating safety critical conditions. And we have implemented in real time on a displaced micro autobox this nonlinear model predictive controller. We are waiting for the end of the lockdown in order to test it on the electric quadricycle prototype available at the ELAF facilities. For the time being, we have comprehensively assessed the performance of our torque vectoring controller implementations of Steve through simulations, so vehicle dynamic simulations. In particular, we have an IEEE transactions on vehicular technology journal paper that is under revision with these results. But essentially, for example, this is a result in an obstacle avoidance test, so an emergency maneuver of the vehicle, and in particular, for two values of friction coefficient equal to 0.9 and 0.7, we are reporting the maximum speed at which the vehicle can pass the test without hitting any cone. And we can clearly see that if we consider the progressively more advanced set of torque vectoring control implementation that we developed during Steve, we can see that there is a progressive increase of the maximum speed at which the vehicle can successfully pass the test. Also, in terms of energy consumption performance, for example, we simulated the energy consumption of the Steve quadricycle along a circuit, and in particular, in this table, I'm indicating with the mouse the percentage energy consumption reduction with respect to the Steve passive vehicle, so with the same torque levels on the left and right hand side of the vehicle, achieved through the progressively more complex formulations of the Steve torque vectoring controller. For example, in this specific circuit, we can see that with the most advanced nonlinear model predictive controller formulation, including adaptation of the weight and the cost function, we have approximately 9% of energy consumption reduction. So this is just to give you an idea. Another topic on which we work quite extensively was the problem of defining an energy efficient speed profile to go from point A to point B with a given time constraint. And to do so, my collaborators ran extensive simulations. Then also they implemented a dynamic programming algorithm to find the absolute optimal solution. And then they designed and tested appropriate controllers. I omit the details here because there is no time, and also there is a published Steve journal paper on IEEE Access regarding these results. But essentially, the main outcome of this activity was the understanding that the so-called pulse and glide driving technique, or pulse and glide control of the torque of the vehicle, is the optimal solution under some conditions for the operation of the Steve quadricycle. Pulse and glide means that if you want to keep the vehicle speed approximately constant during a driving cycle, instead of keeping a constant torque level, we continuously modulate at relatively low frequency the torque between a zero level and a torque level corresponding to the maximum efficiency of the powertrain at that specific speed. So we discovered that pulse and glide was optimal given the data of the Steve quadricycle based on the dynamic programming optimization. And then in cooperation with the LAF, we also tested these pulse and glide algorithms on the Steve JC electric vehicle prototype with the LAF in-wheel motors. For example, here you can see some profiles of the vehicle speed that oscillates with respect to the desired average vehicle speed of 45 kilometers per hour. And we measured the energy consumption per unit distance for the constant speed operation, constant torque operation of the vehicle. And when we implemented the pulse and glide in the Steve quadricycle in the form of a cruise controller modulating the torque between 0 and the optimal level, and we measured an up to 7% energy consumption reduction for the specific test conditions. For example, this is a test where the average speed is equal to 45 kilometers per hour. So I hope that these few slides have provided an idea of the rather ambitious technical developments that have been carried out so far within the STEEP project. Thank you very much for your attention.
Thank you, Aldo.